Alrighty, let's plot some filmetrics data from an oxide run. So when you collect the data using the filmetrics software, right, it just takes one measurement after another. In this context, the first measurement is position 1, then the second is 2, 3, 4, 5 as outlined in the manual, and that's wafer 1. And then 6 would be position 1 of wafer 2, and so on and so on. So in this case, we have 75 measurements, so it's 75 divided by 5, how many wafers there originally were. And you can see that it calculates the mean with goodness of fit, standard deviation, all that good stuff. Now, I could try to write my Python code to delete that and then go here, but I find it just easier to cut and paste it into something called front, and then I share, publish to the web, entire document, comments, separate value. And this isn't sensitive data, so I let anybody have it. And when I publish, right, you just cut and paste, cut this into, let's find it, this code. All right, and you just put it right here in that URL, and it should say equal CSV, otherwise it won't work. So I'm not going to really go into the code too much, except this here is basically skipping every fifth measurement starting at position. The first measurement will be position 1. Every fifth measurement starting at the second wafer measurement will be here, and it will do this automatically to get all the wafers. You just have to make sure that the original number is divisible by 5. And then it'll plot that out, and then it'll take the average per wafer and plot that out, and then see if we can get find a relationship. So I've already run this code, and it just gives you the descriptives on everything. In this case, we had a mean of 494 angstroms with a standard deviation of 26. All right. This is the linear regression. The R squared is 0.13, which is pretty low for a scientific thing, which is in fact what we want. All right? We don't want to find a relationship. And then we come down here to significance. And for the wafer, which is really the position of the wafer, we see that the significance is greater than 0.05, so it's not significant. And what we see is, although it looks like there's something going on with the first wafers, right, which is why we use dummy wafers, right? The gray one is the average of all the positions. The red is position 1, blue is 2, green is 3, and we can see, if it does seem, at least for this run, there is some kind of difference we're getting, right? And then it plots the gray points and the line. And even though it comes up with a line with a slope and an offset, right, there's really not a reliable relationship between wafer number and thickness, which is what we'd want. We'd want it to be tight, but we actually don't want any variance along the length of the tube, because wafer number is effectively wafer position. I forget how many millimeters the wafers are separated by. So anyway, with your data, right, or the class data, you got to put it all in here. So I know some of you did a certain amount of wafers, and then someone else did that, but you've got to put it all together so that you can analyze everything. I'll try to put the code, the Colab code, in the description. That's pretty much it.